welcome back. Our next speaker is Kostya Makarychev, and he's going to talk about algorithms for instance stable and perturbation-resilient problems.
Thank you. So I will continue the controversial theme of beyond worst case analysis started by Uri, but I will talk about a little bit different approach to beyond worst case complexity, about instance stability or perturbation resilience. So this approach got popular recently, and my talk is based on joint works with Harris Angelidakis, Yuri Makarychev, and Aravindan Vijayaraghavan. And first, let me give you some motivation for studying beyond worst case analysis. So as Uri mentioned in his previous work, one of the motivations for studying beyond worst case analysis is that sometimes we can use techniques from algorithms that are developed or designed for beyond worst case instances, then later on to attack worst case instances. Another reason why we may study beyond worst case analysis is that sometimes, in practice, we need to solve NP-hard problems. And actually, often we need to solve NP-hard problems. And of course, we can design polynomial time algorithms that always solve such problems. But maybe we don't even care. So in practice, we only need to solve real-world problems. So instances that come from real world, and we want to design algorithms that work well in practice, and often that's possible. So often heuristics that people use in the real world work pretty well, and they work much better than what's theoretically possible for worst case instances. And so what we want to understand is why it happens. So that's a question we want to ask as scientists. As engineers, we want to design algorithms that work in the real world, and we want to have provable guarantees for such algorithms. But of course, to study algorithms in the real world, we need some kind of model of real world or of real-world instances. And there are many different models of real-world instances, and all of them have some advantages and disadvantages. And Uri talked about various generative, random, semi-random models. I will talk about a slightly different model called stability. I think that's important to have various models because for some problems, one type of models works, for some other problems another type of models works, and even depending on the applications, depending on the source of data, we may need to use different models. So what I'm going to talk today is an assumption called instance stability or perturbation resilience. So these two terms mean exactly the same, but they used in a little bit different context for historical reasons. And I will demonstrate algorithms for stable and perturbation resilient problems on k-means, k-median problems, max cut, and multi-way cut problems. So the first two problems are clustering problems, and the second two problems are sort of graph partitioning or combinatorial optimization problems. So what I'm going to do, I will give two algorithms that find exact solution for these NP-hard problems, assuming that the instances for these problems are too stable or too perturbation resilient. And I will remind you the definitions of these problems, and I will also give you the definition of stability and perturbation resilience in a moment. So let me first remind you what the k-means and k-median problems are. So these are clustering problems. So we are given a metric space X with a distance function d, and our goal is to partition our metric space into k pieces, into k clusters, C1, etc., Ck, and in every cluster pick a center Ci, so as to minimize the sum of distances from every point to the closest center in the k-median problem, and the sum of square distances from every point to the closest center in k-means problem. So often these problems are studied when X is embedded into the Euclidean space, and so the metric is induced by the Euclidean space. And in this case, people usually pick centers from the Euclidean space itself, not from X. So for the purpose of this talk, we assume that we are only given a metric space X, so it's not embedded anywhere, and so we must pick centers from the set X only. So all centers must belong to X. So these are the problems. The multi-way cut problem, which Roy talked yesterday, is the following problem. We are given a graph G, and we are given a set of terminals T1, etc., Tk. And our goal is to partition our graph into pieces so that every piece contains exactly one terminal. And the goal is to minimize the weight of cut edges. So we will deal with k-means, k-median problems, and multi-way cut problem in this talk. And now let me give you the main definition that we are going to study, the definition of instance stability and perturbation resilience. So consider an arbitrary problem, clustering or combinatorial optimization problem, and let's look at an instance I of this problem. We say that I prime is a gamma perturbation of this instance if in I prime all parameters are perturbed by a factor at most gamma. So what does it mean for our two problems? So for multi-way cut problem, any perturbation I prime of our original instance I is defined on the same graph G with a set of terminals with a new set of edge weights W prime E. So every W prime E is sandwiched between the original weight WE and gamma times WE. For our clustering problems, a perturbation is the perturbation of the metric. So a new instance is again defined on the same set of points, but with a new distance function d prime, such that the distance between any two points u and v is sandwiched between the original distance between u and v and gamma times that distance. And now what we require is that we say that an instance is gamma stable if for any perturbation of our instance, the optimal solution doesn't change. So the optimal solution of any perturbation is the same as the optimal solution to the original instance. And there are some subtleties in this definition, and I will discuss them later on. So when we talk about clustering, I will point out to some subtleties and what it exactly means that the solution doesn't change.
You're assuming there's a unique solution. You're assuming there's a unique optimal.
Yeah, that's a good thing. So let's look at this definition. So if gamma is small, this definition is fairly weak. So it means that there is only, so essentially one stability means that there is a unique optimal solution, and therefore kind of pretty much any instance is one stable. At least if you slightly perturb the coefficients, the solution will be unique. So pretty much any instance is one stable. It's a weak condition. As gamma grows, this condition gets stronger and stronger. So in general, of course, we want gamma to be maybe 1 plus epsilon. So this is most reasonable assumption. And also you may think that this condition is very strong because it says that the solution doesn't change at all. So there is a more natural definition, a weaker definition of weak stability, where we say that when we perturb our coefficients, the optimal solution may change, but it doesn't change much. But I won't talk about this definition today. And
Is there a way of like generating such instances?
Why a random model? I don't know. So I don't know whether if you take some distribution, some kind of GNP distribution, something else, whether you'll get stable instances. Probably you can come up with parameters that will generate such instances, but yeah, I'm not sure about this. Okay, so this is the definition. Any questions about it? And now probably you're curious why do we care about stability? Why can we assume that in practice we have stable instances? And the answer is that usually when we look for some solution, you're looking for a solution that kind of stands out among others. And this is the solution that will be optimal. In fact, if you solve a clustering problem, usually you don't care as is about the objective function. So you want to find a good clustering of your data set, and then you try different objectives till you find an objective that helps you to find the clustering you're looking for. And so what happens if your instance is not stable? So if your instance is not stable, you will have always some noise in your data, and depending on that noise, you will get very different clusterings. So in some sense, if the instance is not stable, then you even don't care about solving the problem, because the solution you are going to find won't be relevant to you. So in a way, we only care about solving a clustering problem if the instance is stable. Of course, this condition might be a little bit strong, so it's kind of only approximation to what we want, but this is the idea why we care about stability. Maybe we need to slightly relax the conditions of the stability, but that's a good open question actually, how to make it a little bit more realistic. But the idea is that if you have a non-stable instance, that you will get very different solutions because of minor variances in your data, and those solutions won't be the solutions you are looking for. Okay, so let me give you an overview of results and kind of history behind this question. The notion of stability was introduced by Bilu and Linial in 2010 in the context of discrete optimization and specifically max-cut problem, and then it was adapted for clustering problems by Vaithe, Blum, and Sheffet in 2012, and so they studied k-means, k-median, and k-center problems. There were some related notions, but are somewhat different, and I'm not going to talk about them, by Ostrovsky, Rabbani, Schulman, and Swamy, and Balkan, Blum, and Gupta. So what's known about clustering? So for clustering, Vaithe, Blum, and Sheffet first proposed an algorithm that finds the exact solution for 3 stable instances of k-center, k-means, k-median, and some other problems. The result was improved by Balkan and Lian for gamma approximately 2.41. And then Balkan, Khattalab, and White gave an exact algorithm for symmetric and asymmetric versions of the k-center problem, where gamma is 2. And Harris, together with Harris and Yuri, we gave an algorithm for 2 stable instances of k-means and k-median. And this is the algorithm I'm going to talk about today. And so note that this result of Balkan, Khattalab, and White is essentially tight. That's what they showed. And the other results might be tight or may not be tight. So they're tight under some other assumption, which is called center proximity. And they will talk about this assumption. So it's not clear whether this result can be improved, and that's, again, an open question. So what's known?
So with this resilience, do you still only restrict to that the modified input still is metric, or does it have to work for things that are then sort of? Yes,
that's an excellent question. So you can restrict it only to being a metric. I will talk about this, but yes, you can restrict it only to be a metric. In the original definition, the perturbation could be an arbitrary set of distances, not necessarily satisfying triangle inequalities. So for combinatorial optimization, Bilu and Linial in the original work showed how to solve exactly max-cut instances with gamma equal c times n. So this is a very strong assumption on stability. And then they slightly improved it in the work with Danieli and sags to gamma equal to c times square root of n, and here is the number of vertices. So we exponentially improved it with the work in the work with Yuri and Aravindan to gamma equals square root log n log n, and we kind of showed that this might be optimal. So we gave some evidence, not very strong evidence maybe, that this is optimal bound. So in a way, this result might be a little bit unsatisfactory because still gamma is pretty large. So generally, we want gamma to be much smaller, but situation is much better for multi-way cut. So in the same work, we gave an exact algorithm for gamma equal to 4, and in the recent work with Harris and Yuri, we improved it to 2 minus 2 over k. And if I have time, I will tell you a little bit about this algorithm as well. But now let me show you an algorithm for clustering problems, k-means, k-median, and actually many other problems. So here is the plan. First, I will prove that gamma perturbation resilience imply another property called gamma center proximity. And then we will see that if our instance satisfies two perturbation resilience and hence to center proximity, then the optimal solution looks very nice. So each cluster in the optimal solution is a subtree of the minimum spanning tree. And using these two properties, we will design an algorithm. So the algorithm works as follows. So it takes the metric space X, then finds the minimum spanning tree. And in this minimum spanning tree, using dynamic programming, it recovers the cluster CI. So that's going to be the plan. And OK, the first step in our plan is this. We need to show that our instance is satisfies two-center proximity. What is center proximity? We say that an instance satisfies gamma center proximity if for any cluster Ci and every point P in that cluster, the distance to the to any other center, to any center outside of its own cluster, is at least distance gamma is larger than the distance to its own center by a factor at least gamma. Again, so we take any center Ci, any point P, and look at the distance from P to any center other than its own center, and this distance must be gamma times greater than the distance to its own center Ci. So this is a property, OK, so now I'm going back to David's question. So what is perturbation resilience? So in perturbation resilience, we say that any perturbation of our metric should keep our optimal solution intact. So it shouldn't change the optimal clustering. And here, I need to point out that it shouldn't change the clusters, but it can change centers. If we say that any perturbation doesn't change centers as well, it will be too strong condition. And in a way, all the result would be meaningless. So an important point is that any perturbation doesn't change the clusters, but it may change centers. Another subtle point, whether the new metric D prime should satisfy triangle inequalities. And in the original definition, it didn't have to, but we put another constraint on it that D prime must be a metric. And this, of course, makes the definition only weaker. And so if an instance satisfies the original definition, it will also satisfy the new definition. So we will work with this condition. So let's prove that perturbation resilience implies center proximity. And the idea is as follows. So let's assume that this is not the case. Then there exists a point P and a center Cj such that the distance from P to Cj is less than gamma times distance from P to Ci. Let's perturb the metric and decrease the distance from P to Cj to be equal to the distance from P to Ci. since this ratio was less than gamma, this is the gamma perturbation of this distance. And let's not change other distances. So if we could make such a perturbation, then we will be done, because we know that our instance is perturbation resilient. It means that the optimal clustering doesn't change, and it means that the distance, and it means that P still belongs to the same cluster as before, which implies that the distance from P to Ci is less than the distance from P to Cj. Otherwise, we could move P to another cluster, and we would get another optimal solution. However, there are several problems here. So one problem is that when we decrease the distance from P to Cj, then it may affect some other distances, right? So if we only change that distance, then the new metric won't satisfy triangle inequality. So what we do here is that we decrease this edge, the length of the edge from P to Cj, kind of in the complete graph on our metric space, and then we take shortest path metric on the graph. So if we take the metric closure, and of course by the definition it satisfies all triangle inequalities. However, now we have another problem. So once we make this closure, the distances within every cluster may somehow change, at least a priori, and because of that, the centers of the clusters may shift. And so the previous argument doesn't work. So it turns out, however, that the distances in the clusters, within the cluster Ci and Cj do not change. So let's see why. So let's pick any 2 points U and V in Ci, and let's look what's the distance between U and V in the new metric. So this is a minimum between the original distance between U and V and a kind of shortcut taken over this edge PCJ. So it's minimum between DUV and the distance from U to P, then the new length of the edge PCJ, and the length of the edge between V and Cj. Let's look at this new distance. It's low bounded by the length of the path from U to P, then from P to Ci, and from Ci to V. Why? Because the distance from P to Cj is equal to the distance from PCI, and the distance from V to Ci is less than the distance from V to Cj because V belongs to Ci, and Ci is its own center for V, right? So the distance from V to Ci is smaller. So we got that the distances in Ci didn't change, and similarly the distances in Cj didn't change. So it means that the centers of the clusters remain the same. And so the argument I gave you before works now. So since P belongs to the cluster Ci, the distance from P to Ci in the new metric is less than the distance from P to Cj. So we proved the statement. Now we need to show that the optimal clusters form subtrees in our minimum spanning tree. So the picture looks like this. So why does it happen? We will use a lemma from ABS that says that to proximity implies that for every cluster Ci and for every U, the distance from U to its own center is less than or equal to the distance from U to any other vertex, not from any other point, not in the cluster Ci. So before that, we had a condition that the distance from U to its own center had to be less than or equal to half of the distance from U to any other center. And here we kind of relax this condition, so we are interested in the distance from U to any other vertex, but we lose the factor of 1/2. And this lemma is easily proved by applying triangle inequalities. So I will skip it. And now what we have? So we need to show that for any vertex U, the unique shortest path in the MST from U to its own center Ci lies within the cluster, right? So assume that this is not the case, and that there is an edge, there is the vertex U such that the path from U to Ci leaves the cluster Ci, and let's assume that UV is the edge that crosses the boundary of the cluster. And then, of course, what we can say is that by this property, the length of the edge UV is less than or equal to the length of the edge from U to Ci. And because of this, we can replace in the MST the edge UV by the edge UCI. And this will only decrease the length of the MST, and we get a contradiction. So we showed the statement. And now we need somehow, so what we now know is that all clusters, all optimal clusters are subtrees of the MST. And to recover these clusters, we use dynamic programming. So for every subtree, we just will store the price of dividing that subtree into j pieces. And we should be a little bit careful with the top part of every subtree, sort of this cluster, which U belongs to, may have a center outside of the tree. So we will add another parameter. So what we'll store for every U, J and C, we will keep the cost of breaking that subtree rooted at U in J pieces, given that the cluster which U belongs to should have a center in C. So this is our dynamic program, and it's not hard to show that by filling the DP table bottom up, we can solve the DP. So we need to consider various cases where different subtrees of U belong to the same to the same cluster as U, or different clusters. So it's the same. One of them is the same, the other is not, etc. And we can write a recurrence like this, which is correct, but probably you don't have time to fully understand what's written here. And sort of this solves the problem. So again, what we showed is that an algorithm which is often called single linkage algorithm, and that was used from early 60s together with a new dynamic program, solves the k-means problem and k-median problems, assuming that instances are too stable. Of course, this assumption of too stability is very strong. So how much time I have? OK, so let me then give a summary. So I showed you how to solve the problem, clustering problem for two perturbation-resilient problems. There is another algorithm that solves a multi-way cut problem, and the algorithm itself is very easy. So we just write the standard LP relaxation for multi-way cut, and solve it. And it turns out that if the instance is too stable, then the solution is integral. So we just output the integral solution. That's easy. The interesting part, of course, how to prove that instance is stable. And surprisingly, we need to design an approximation algorithms for the purpose of the proof that kind of is a witness of stability of the optimal LP solution. We also showed various negative results. And so I think the most interesting open question is what's the right definition of stability, how much we can relax it, and whether this assumption is kind of realistic and to what extent. And so, thank you.
So I'm assuming that the algorithm on a worst case instance with a bad approximation ratio, this particular algorithm, or any
OK, so for clustering, right? So for multi-way cut, it's NLP, so it has the same approximation ratio as the best algorithm for multi-way cut. For stability, yeah, so I think you can come up with pretty bad examples.
So the question then is, can there be an algorithm which is some maybe log n factor for k-median, but is exact for the
Yeah, that's a good question. I mean, there is, of course, a trivial thing, try two algorithms and take the best. But if you care about a more natural algorithm, I don't know. But the nice thing about this algorithm is actually that such algorithms are used in practice. I mean, not exactly like this, but the idea is called single linkage, and single linkage is used in practice. Even though I think, it's very easy to come up with bad instances. You can kind of come up with some kind of bridges. Pretty much for any instance, if you let me add a little bit of outliers, I can fail this algorithm.
Awesome.
So, I mean, it seems that you're sort of stuck in a conundrum in that you can test whether an input is too perturbation resilient. So it would be nice if, on the flip side, you could have a certificate of optimality, at least on an instance by instance basis, which it doesn't seem you have. Let's say for the clustering one you just did. Do you think there's any hope of let's say even just for that?
Yeah, I hope. In fact, what we want so-called robust algorithms. So what we want is that either the algorithm solves the problem exactly or finds a good approximation depending on the guarantees, or it says, okay, this instance is not stable. So there may be some gray area where the algorithm still solves it, but the instance is not stable. That's fine. And for our combinatorial optimization problems, of course, the algorithm is like that because it solves the LP. And it says, okay, if the LP is integral, then I give you the solution. So obviously the solution is optimal. For clustering, we tried to come up with robust algorithms as well. So far we don't know how to get a robust algorithm.
Is the LP good on two stable clustering instances?
I don't know.
Okay. Other questions?
So, yeah, is there a smooth degradation? So like okay, because you're saying we want 2 stable, but suppose I give you 1.5 stable, maybe don't give me exact algorithm, but maybe 1.1 approximation, things like that.
Probably no. I need to. No, I don't think so. At least not for clustering. No, not for this clustering algorithm, I think.
Okay, then let's thank Kostya again.